In this video, we will talk about the acceleration of short-range MIMO imaging systems with an optimized Fourier processing technique. My name is Thomas Fromentez, and this work was prepared in collaboration with Fabien Berland and Cyril Decroze from the University of Limoges, with Okan Yoduseven from Queen's University Belfast, David Smith from Duke University, and finally Alexander Yaovoy from TU Delft. This video was recorded for the Passive and Active Millimeter Wave Imaging Conference in the framework of the SPIE Defense Commercial Sensing Digital Forum 2020. To introduce this video, we first have to define what is MIMO imaging, which stands for multiple input and multiple output. In this context, we are looking at the interaction between a transmit array of location xt and a receive array of location xr. We are trying to image a target set in the region of interest, defined by reflectivity sigma. To do so, we first have to measure the interaction between all the transmitters and all the receivers to extract the response of the target. We use free space Green functions for modeling this interaction, accounting for the radiation of spherical waves from the transmitters and the receivers. To facilitate the reconstruction that will next occur, it's sometimes preferable to group all the propagation terms into a single operator like that. To complete this part, it's finally interesting to mention the simplest but also quite inefficient imaging algorithm, which is the delay-and-sum backpropagation applied directly on the MIMO dataset. The following expression is then defined, achieving the backpropagation by using free space Green functions, but now removing the minus sign on the phase part. This expression can be even further simplified because the magnitude terms can have a negligible contribution to the total summation. By discretizing space like that, we can backpropagate the waves for a given couple of transceivers, and we see that pixel by pixel will achieve this backpropagation. This operation can be really intensive for the numerical part because we have to do that for all the couple of transceivers and all the frequencies, making the reconstruction of the image possible. Facing these limitations, we can now study more advanced reconstruction techniques like the range migration algorithm, which is also referred sometimes as the omega k algorithm and the angular spectrum method. All these different names do not facilitate bibliographical research, so I will only use the term RMA throughout this presentation. To start the explanations on why the range migration algorithm can be so efficient, we look at our initial problem where we have a transmit array sending a wave toward a region of interest, and the wave is then reflected back to a receive array. To facilitate the first explanations, we only keep the transmit array and the point target is transformed into an isotropic source. We then exploit the reciprocity principle, now considering that our antennas act as receivers. The key here is to consider that the isotropic antenna is radiating spherical waves that can be decomposed into a sum of plane waves in the context of the range migration algorithms. At a given frequency, the rigorous development is given by Wells expansion, where our Green's functions is decomposed into a sum of plane waves defined by their k-vector components. And we will see that the k-vector projection along the optical axis will play a critical role in this technique. At this stage, we can wonder how this technique can be useful to us because it looks more complex than the initial delay-and-sum backpropagation. To illustrate that, we can find an interesting application to synthetic aperture radar in the following reference. So to get back to our initial problem, we are trying to localize a source in space according to the received waves on an antenna array. The source localization is achieved with the measured signal expressed here in the frequency domain, which undergoes a Fourier transform to work with plane wave components. The backpropagation is finally achieved by compensating the phase of plane waves, replacing the expression of the longitudinal axis component ky by the dispersion relation shown here. If we are using a uniformly sampled array, this operation can be really efficient by using fast Fourier transform for this first step and for the inverse Fourier transform here. But because the ky component is non-uniformly sampled, we are limited to using a direct Fourier transform, or we can speed up this process using an interpolation and a fast Fourier transform. This interpolation, as defined by Stolz, can be explained graphically. We first draw the initial domain in which our signal is defined, considering that our frequency dimension can also be expressed as the k wave number component if we are propagating in free space. Because the relation between the k vector and the ky component is nonlinear, we have to find a way of interpolating this dimension into a uniformly sampled domain. It can be done by realizing that our isofrequency ky contour are defining circles on which we will project our dataset. Our data is now uniformly spaced in the plane wave domain and can undergo a two-dimensional fast Fourier transform to speed up this process. So now that we have seen how to perform the range migration algorithm for a localization case, we can get back to our initial MIMO problem where we have a receiving array. MIMO imaging starts here by the measurement of the interaction between all the transmit and receive elements. In a similar fashion to what was presented before, we transform our dataset using a two-dimensional Fourier transform to express the location of antennas in terms of plane wave components. Backpropagation is achieved once again by compensating the phase of plane waves. However, because our problem is now defined by the interaction between transmit and receive plane waves, we have to define composite vectors corresponding to the sum of the transmit and receive ones. This principle was proposed in the following reference where they adapt the range migration algorithm to MIMO imaging, and the formalism is of course simplified here because I only have two dimensions. Even if this technique is really efficient for computing 3D images with a MIMO system, it is still facing limitations. And the first one we'll mention here is the problem of non-uniform sampling of the transverse wave vectors. The sampling of the transverse wave vectors is indeed directly defined by the sampling of the transmit and receive arrays. And even if both arrays are uniformly sampled, we cannot guarantee that the sum of their transverse wave vectors will create a uniformly sampled kx vector. To remain compatible with the use of fast Fourier transforms, we'll then have to use interpolation techniques in this context. How we can simply conceive transmit and receive arrays such that their equivalent kx vector will be uniformly sampled directly. The second limitation is slightly harder to understand and is about the way we do the plane wave sensing. When we work with plane waves, we are performing an operation similar to beamforming, filtering out the radiation in a given direction of space, defining a k vector. And to be more precise, we only define the transverse projection of it on our array, then deducting its direction from the norm of the vector defined by the frequency. We now know that we can retrieve the transverse projection of a k vector, but we are actually limited by the spatial extension and sampling of the array. And because of that, our initial delta function is convolved by the Fourier transform of the field in the aperture, limiting our angular resolution and sometimes creating artifacts due to grating lobes. Our goal in this context is then to propose a Fourier domain technique that overcomes these limitations of non-uniform sampling and plane wave sensing, while remaining fast and accurate. Finally, I can introduce the transverse spectrum deconvolution, or TSD-RMA for short. Returning to our initial problem, we now consider that each array is associated with its own plane wave spectrum defined by its spatial sampling. The novelty here is that we also consider the target response, expressed here in green and in the Fourier domain. In this new perspective, the dataset at a given frequency actually corresponds to the interaction between the transmit and receive radiation patterns and the spectral signature of the target, expressed as function of plane wave components. For each sample, a new direction of space is then probed by one of our two patterns. It seems important to precise that the spectral response of the target does not, of course, depend on the complex weights applied to the array for these beamforming operations, and therefore remains constant throughout the entire measurement. We can finally consider that our measurement corresponds to the interaction between the radiation patterns in transmission and reception with the spectral response of the target propagated to the arrays. To simplify this expression, we can create a single operator corresponding to the radiation of the complete MIMO system and discretize it according to kx in order to propose an equivalent matrix formalism. The propagated spectrum of the region of interest can finally be estimated by means of pseudo-inversion, and practice shows that a simple conjugate transpose operation can offer good performance. To conclude this explanation, I must insist on the fact that the main advantage of these reconstructions is that they are independent of frequency, the latter defining only the limit between propagating and evanescent wave vectors. We finally end up with a formula very close to the one previously introduced for short-range MIMO imaging. The processing is simply optimized here, as the data used for backpropagation were estimated by taking into account all the lobes constituting the transmit and receive radiation patterns rather than only one direction for each sample. A new dispersion relation for Ky can be determined, corresponding to the following formula, since we now have merged all the information on the same Kx axis. However, this dimension is still not uniformly sampled according to Ky, and it is therefore necessary to use the stalled interpolation tricks presented earlier. We can finally extend this principle to 3D imaging by adding a z-dimension to our antenna arrays and updating our expression as follows. We have now seen all the theory behind this new imaging technique, and we can move on to the results. The application of these techniques is motivated by a particularly complex case adapted from our work on computational imaging. In this context, secondary radiating elements interact in transmission and reception, before an analog coding technique multiplexes all its information into a single measurement signal. The connection with the operation of conventional MIMO systems has been demonstrated in earlier work, and here we focus on the particularly unfavorable case of densely populated radiating apertures used both in transmission and reception. The validations proposed here are based on numerical simulations, first studying the imaging of 9 scatter points located at 50 cm from our array. The latter is made of 40 antennas per side, and the array is used for both transmission and reception of electromagnetic waves. We work at each frequency with more than 2.5 million interactions between antennas that we'll have to exploit for the reconstruction of images. Considering K-band signals composed of 20 frequency samples, we thus arrive at a total of more than 51 million measured samples to be processed as quickly as possible. A first reconstruction is performed with the original MIMO array technique and is compared with the results obtained using the proposed method, which can then be coupled with stalled interpolation to speed up the reconstructions. It can be seen that the fusion technique proposed here allows a more accurate reconstruction of the position of the target points, especially those located closest to the array. It's important to note that the results presented here do not use any spatial preconditioning of the signals by zero padding or interpolation to accelerate the reconstructions, justifying the performances observed for the initial algorithm. By comparing the reconstruction times for different sizes of antenna arrays, it can be determined that the computations are performed much faster with the proposed techniques. Accelerations go from a factor of tens to several hundreds depending on the size of the data to be processed, facilitating possible real-time imaging applications for large systems. I conclude this video by discussing a practical application of this technique in the case of a microwave body scanner. These applications take advantage of the near transparency of clothing at these frequencies to reveal the presence of hidden objects such as firearms carried by people. Here we have an array of 71 antennas per side, operating in the same frequency band as before. One measurement now consists of more than 1.2 billion samples that will have to be processed for image reconstruction. Being limited by the memory conception of the original MIMO array technique, only the proposed TSD approaches will be applied here. We can see that the reconstructions allow in each case the identification of the weapon carried by the target, facilitated by the use of color coding corresponding to the depth of the reconstructed voxels. The use of interpolation technique allows a slight acceleration of the reconstruction, but we can see in each case that fast Fourier transforms now represent a significant fraction for each reconstruction. The computation times on this personal computer are still important, but must of course be put into perspective with the dimensions of the problem studied. It seems realistic to imagine a transposition of these techniques on more powerful and highly parallelizable computing systems, suggesting possible real-time applications of these techniques. In this video, I had the opportunity to present a new technique to improve and accelerate the reconstruction of images from short-range measurements by MIMO systems. I would like to thank all my co-authors, whose institutions are shown, for their contribution to this work. I would also like to thank Grant Sanderson from the YouTube channel 3Blue and Brown, who provided the Python animation engine used in this video.